Hey, what's going on, guys? Let's do this problem right here. The first question is asking the pressure of a gas inside a rigid 2.4 liter cylinder is decreased from 4.8 atm to 3.4 atm. How much work was done by O on the gas? So let's see how we can find it. So if you notice that this is a 2.4 liter cylinder and the volume is not going to change. So whenever we have a condition that volume is constant, that is an isochoric process. So this is we call isochoric process. For an isochoric process, the work done is always the uh, the work is always zero. If you want to make sense of this one, we can go ahead and use W is equal to P delta V equation. And if you see that pressure is changing, but delta V final minus initial, so it's going to be same volume and you will get 0 for that, and if you multiply 0 with pressure you will get 0, so work done here is 0. So for an isochoric process it's always 0. So the question is asking how much work was done or on the gas, so the work done is 0, so that's the answer for this question. And let's do this question right here. The second question is asking how much heat energy is required to increase the temperature of 7 moles of each of the following gases by 50 Kelvin. Okay, so let's look at the first one. Helium at a constant volume of 5.4 liters, so constant volume. So in this condition, in this situation, what equation we are going to use? So if you think about it, we know that this is isochoric process, but they are talking about the heat energy. So for heat energy, there are different equations. For if it's constant volume, we use Q is equal to NCV delta T, and if it's constant pressure, we use Q is equal to NCP delta T. So here they are talking about constant volume, so we are going to use the first one. So let's use the first one. Q is equal to NCV delta T, and we know the mole that is provided, 7 moles. So we can apply that one right here, 7 moles. So NCV, what is the NCV value for this one? So NCV value is basically is provided in the book. If it's not provided, you can find it by using this formula. For a monoatomic gas, the NCV value is basically 3 by 2 multiplied by R. R is a 8.31, that value. So if you multiply that by that one, you will get this CV value. And for helium, it's provided, it's a monoatomic gas, so you can use this number, that is 20.78. 78 multiplied by the temperature change, that is already provided, so we don't have to separately calculate. So since the temperature change is provided, we don't, this is not useful for us. The volume or a pressure is not useful since the temperature is provided. So we can directly calculate this one, and if you calculate, you will get 4 times 3 okay, wait a minute, it's 4364.5 joule, right? And for this one the unit is joule per mole Kelvin. Joule per mole Kelvin, right? So here we have to put joule per mole Kelvin. So this is the coming like this. This is the value for this one. So let's do the B part. The B part is asking argon at a constant pressure of 9.2 atm, and what is the heat energy. So here they are talking about constant pressure, so we are going to use this equation right here. Q is equal to NCP delta T. Q is equal to NCP delta T, and for monoatomic gases, the Cp value is always going to be 5/2 times R. But for argon, you can look it at the book, so you can get the value from the book, that is 20.76. Here they have given the moles right here, that is 7 moles, so we can directly plug it. 7 moles times Cp is 20.76 joule per mole Kelvin multiplied by the temperature change, that is provided 50. So that is 50 Kelvin, and if you calculate this value you will get 7266 joules. So this is the answer for the B part. Let's do the C part. So C part, they are asking N2 at a constant volume of 0.50 meter cube. So N2, this is a diatomic gas, so we have to use different value. So they are saying it's a constant volume, so we are going to use the first equation, Q is equal to NCV delta T. So let's use that one right here. Q is equal to NCV delta T. N is provided 7 mole. So for diatomic gases, the CV value is 20.76. 20.76. Also, you can calculate this value using 5/2R. So it will give the similar value. So let's multiply by this value. This is joule per mole Kelvin. So 27 mole multiplied by 20.76 joule per mole Kelvin times the temperature difference that is provided, that is 50 Kelvin. And if you calculate this value, that will give you 72. This is 7273. This is 72766 joule. And let's do the D part. So D part right here, it's asking CO2 at a constant pressure of 1.4 times 10 to the power of 5 Pascal. So constant pressure, so we are going to use the second equation, that Q is equal to NCP delta T. Q is equal to NCP delta T and 7 mole. And here if you notice we have triatomic gas because we have 3 atoms, carbon, 2 oxygen. So it's a triatomic gas. So to find the pressure in a Cp in triatomic gas, you can use 9/2 times R, right? So for a monoatomic 5/2, for a diatomic 7/2, for a triatomic 9/2 R. So that's how it goes. And Cp for this one, you can look it from the book, you will get 36.94. So 36.94 joule per mole Kelvin times the temperature difference that is provided, 50 Kelvin. And if you multiply everything, you will get 12,929 joule. And that is the final answer. I hope you guys like this video. See you next time.